run around simulations of galaxies, their gas halos, and large-scale environments, and he works at the interface between theory and observations, building open source software for data analysis and visualization that many of us are using in the field. Cameron got his PhD from Columbia, then he moved to University of Arizona as postdoc, and then to Caltech as an NSF fellow, where he is now a research scientist. Apart from research, Cameron is also an avid science educator. He is a director of astrophysics outreach at Caltech. He was astronomer in residence at the Grand Canyon last fall. And he was also consultant for a number of Hollywood movies, which you can ask him later.
They're not very good. But it's not my fault.
We'll talk about it. Okay, apart from science, you are most likely to find Cameron outdoors, pushing the limits of what a human being can achieve. As a fun fact, Cameron holds a world record of crossing Death Valley on foot. He covered the distance of 170 miles in the desert over 4 days, or 4 days, thereby not only breaking the previous record, but breaking it in half. So if you, in the unlikely event you run out of scientific topics to discuss with Cameron, you can always ask him about his adventures. Okay, without further ado, please take it away.
Thanks, Vadim.
Can you guys hear me okay? Or is it too clicky? Okay, it's all right. Yeah, so thank you, Vadim. Thank you guys for hosting me. I primarily want to talk about the circumgalactic medium and how computational models of it can potentially reveal a great deal about galaxy evolution and the formation of structures in the universe. So just a broad outline of the four kind of main topics that I'd like to cover. A basic introduction on the circumgalactic medium, although it's probably not too necessary here, but I'll kind of speed through that. How we actually forward model the CGM and the radiative transfer of observations of it. Why are simulations bad at modeling it? I'll give you a preview on the various things related to that, and then what can we actually do to ameliorate this issue. So just broadly, what's the CGM? It's the gas, the low-density gas that fills the galactic halo beyond, potentially out to the virial halo, the virial radius and beyond. So it's fed by a number of different physical processes, both internal processes in terms of galactic outflows from AGN and from stellar feedback and supernova and whatnot, as well as external accretion from the cosmic web and from other galactic structures. So it's really crucial to understand the behavior of this reservoir of gas because it's probing all of these different physical processes as well as fueling the galaxy and providing it with fuel for star formation, which can determine its overall kind of evolutionary track. Traditionally, observations of the circumgalactic medium have had to rely on background objects and absorption line spectroscopy, primarily because this gas is so low density. Because emissivities go with the square of the density of the medium that you're probing, it's very difficult to see through conventional telescopes and conventional techniques, see it in emission, although that's changing, and I'll talk a little bit about that during the luncheon talk. But the primary way in which we observe this is through absorption line features. You have a bright background source like a quasar that you take a spectrum of, and then you observe the various different absorption features that are in that, and that gives you some idea of the trajectory, or the phase of the gas along the path of that sightline, as you can see in this sort of cartoon. Now, these various features, nitrogen-5, silicon-4, O6, silicon-3, various different ions that probe the phase of the gas along that path. If we look at a phase diagram where you have density, gas density on the x-axis and temperature on the y-axis, you see the gray shaded is essentially comes out of a simulation, but the various different ions populate this space. So you have what are known as low ions, i.e. low ionization potential ions that don't take a lot of energy to excite them, sitting down here in the dense, cool region of phase space, whereas more highly ionized potential ions, the high ions, sit in lower density and higher temperature space. So you can put together what an entire galactic halo might look like. Of course, we don't have a million different quasars that sit behind a galaxy so that you can probe a single galaxy this way. So it's really a stack of population statistics of various different sight lines through different halos that are heterogeneous in the distribution and in the sample. And so you essentially put together this radial profile plot where you have a projected radial distance of your sight line to some sort of central galaxy, and then the equivalent width of those various different absorption features, and you can put together something like this. So you've got projected distance from the center of a galaxy on your x-axis, and the strength of a particular ion on your y-axis, in this case, the column density of oxygen-6. This is from the COS-HALO survey that originally started putting stuff out in 2011, but has since added to that over the years. And you can see some sort of radial distribution. In this case, star-forming galaxies have pretty much standard 06, regardless of their distance from the center of the galaxy, whereas passive galaxies, it's a little less clear, but it seems to be lower. And you can do this for a variety of different ions that I talked about, neutral hydrogen, various different carbon lines, silicon lines, oxygen lines. And people have done this. This is purely from observations. And it tells you something about how quickly not only these metals fall off with distance from the center of galaxy, but also what the phase structure of that galaxy is. But it's making a lot of assumptions, right? Like you have, as I said, you have a heterogeneous distribution of galaxies that you're choosing from, and so it gets a little messy.
Excuse me?
Yeah.
From your plots, it looks like there is an intergalactic component because it does flatten at some value.
You're right. There is an intergalactic component, particularly in the neutral hydrogen because of the cosmic web and these sorts of structures. And we see neutral hydrogen extend to very, very large distances, primarily from the IGM. You're absolutely correct. Less so with the metals, less so especially with the low ionization potential metals, partially because metals we don't think exist quite as far out, but also because that's probing cool gas, and generally in the IGM you're getting a lot of photoionization from the radiation field that's out there. So there is a general kind of consensus picture that is kind of visualized here. You've got your galactic disk and perhaps outflows along the semi-minor axis, and then inflows potentially along the semi-major axis. But there are a lot of remaining questions about this sort of consensus picture that we can't easily probe through the conventional mechanisms that we use to observe this. So what is the origin of the gas? What is the dominant gas coming from internal processes? Is it coming from external processes? How large are the individual cool gas clouds that make up this kind of distribution? And are they in thermal equilibrium with the hot gas, or is there additional pressure support terms from magnetic fields or cosmic rays? What microphysics dominates those flows? And most importantly, what's determining what gets into the galaxy versus what doesn't get into the galaxy, and how that could lead to quenching and production of passive systems or active star formation as the gas flows continue down to the center. So just kind of to reach a consensus about the first part of the talk, the CGM is this massive reservoir of gas around a galaxy, and it consists of these, primarily a cool and a hot phase. They're perhaps in thermal equilibrium between like 10 to the 4 Kelvin gas and 10 to the 6 Kelvin gas, controlling the star formation rate and the overall evolution of the galactic system. So how do we simulate the CGM and compare these results to our observations? So as Vadim mentioned, I work a lot on open source software for the community. These are a few of the different packages that I work on. YT is probably the most known amongst these. It's used a lot in analysis and visualization of generally all computational data sets, but specifically simulations and hydrodynamic simulations. And then these others are for more specialized for analysis and visualization of the circumgalactic medium. So how do we simulate the CGM? Just I'll keep it reasonably quick because I realize this is ITC and there's a lot of simulators here. But we use our simulations to discretize the domain in which we're trying to simulate. In this case, I'm generally talking about cosmological hydro simulations of galaxy evolution, but you could apply this to a variety of different simulation types. And we represent on that discretized fluid a number of scalar and vector fields to describe the distribution and the behavior of the gas. So in this case, in my little cartoon, I've discretized it as a grid, although this equally applies to particle-based modes or moving mesh codes like a repo that's used here. And so we discretize this into scalar elements, or scalar field, and you can have density field, temperature field, and so on and so forth. And then over time, we evolve using hydrodynamic, like the Euler equations, to move that forward and account for gravity and the effects of hydrodynamics over time. And then you end up with a pretty movie like this, where we're showing density, column densities of density on the right, and density-weighted temperature on the, on the left, and density-weighted temperature on the right, and follow the evolution of a Milky Way mass system. So this is from the fire simulations. This is kind of the canonical run of that, and we've followed it from redshift of, I don't know, like 10 to redshift of 0, and we see that slowly this accretes neighboring systems. We see the virial radius expanding as it grows in mass, and I'll just play it once more. You can see the cosmic web and the filaments of the cosmic web that are feeding it, and it's accreting galactic systems over time, and every time a galactic system falls on, there's a burst of star formation and a hot wind, a yellow feature of hot wind that's driven out as these stars form and eject material and metals and energy. So this is all fine and good and fun to watch and get an intuition about, but when we look at the universe, we're not looking at density and temperature scalar fields. We're looking at emission from specific gas, or as I was talking about, we're looking at the absorption features from specific ions. And so we need to post-process these data sets to include the ion fields. There are some data sets that already contain and follow the evolution of various different ions, but these are really expensive to do to integrate the chemical networks on the fly on each individual fluid element. And so what this code that I've generated, Trident, is a way of kind of post-processing and making certain assumptions about the radiation field and the collisional ionization to essentially paint on the various different ion fields from a snapshot after the output. So you can paint on the neutral hydrogen field, or you can paint on the oxygen 6 field, or whatever arbitrary ion that you may care about. And then we can reproduce this very same movie that we watched before, but instead of looking in density and temperature, we can look at neutral hydrogen and oxygen 6 to see the very different phases of the gas that it probes. So neutral hydrogen, very filamentary, because it generally is probing dense, cool clumps of gas, whereas the oxygen 6 is much more diffuse, because it's generally probing hot and low density gas that's kind of this halo-filling component. But we can do this for any arbitrary ion that we might care about. Okay, so it's one thing to produce these maps, and this is good enough for a lot of papers to do relevant analysis. But we can also further forward model the simulations to make a real apples-to-apples comparison with the observations. And that is sending some sort of arbitrary sightline through to approximate the sightline that's taken to a distant quasar or a distant background source, and then probing the fluid and the ions that are along that line of sight. So here's an output from a galaxy simulation and a sightline that we're passing through that. And this is just along that path. It bumps into, in this case, we're just looking at silicon-2. I just chose this as an arbitrary ion. There's some silicon-2 as we pass through the central part of the galaxy, and then a little bit more as we pass through this cloud later on. And then this is just the line of sight velocity of that gas relative to the observer in the corner, which of course is going to affect the redshift of that system. So if we do this again, and we look at the relevant part of the spectral space, we get absorption features as it passes through these various different clumps of material, accounting for the line of sight velocity of that gas relative to the observer. And you can eventually produce these sorts of results. On the top, we have an actual observation. I think this is from high-res, and on the bottom we have, no, this is from the cosmic origin spectrograph on HST, and then on the bottom we have a simulated version of that spectrum just from one of our arbitrary simulations with an appropriate signal and noise that's applied to it. So what happens if we apply these forward modeling methods to our simulations to try and reproduce these sorts of radial profiles of various different ions that the observations have yielded? The result is, in general, the simulations underpredict the amount of stuff there is in the circumgalactic medium. In all three of these cases, the dots or the error bar uncertainty line are the actual data, and then the curves underneath are the simulation. So observations, simulation. And the simulation underpredicts the overall amount of stuff that's there in a variety of different ions. Carbon 4, I think over there's oxygen 6, H1. And while there have been some reproductions where a simulation can reproduce a particular ion, there isn't yet a simulation that can reproduce like all of the ions that we have from observations, which is, of course, challenging. So how do we simulate the CGM and compare to observations? Use a variety of different tools, and I've tried to make these as open source and useful for the community instead of just for myself to get work done. And in general, simulations historically underpredict the overall amount of material in the circumgalactic medium.
Just to be
Yeah.
clear, the underprediction is both for the low and the high ions?
It depends on the model, but yes, in general, it's for both the low and the high. In general, you can do a better job of getting low ions if you have a non-thermal pressure support term, like cosmic ray feedback has been very effective at that. But then there are problems. There's a lot more cool gas, but there's a lot less hot gas. And so the higher ions are much more challenging to observe. So it's kind of like there hasn't yet been a way of getting all of the things all at once. Yes?
One difference between observations and simulation is that in the observation you are integrating along the line of sight.
Yes.
And there could be a lot of contribution from outside of the galaxy that has nothing to do with the outflow there.
That is true.
So how do you account for that? Because I see that some of the observations, they look flat.
Yes.
If you go back one
Yes,
step.
that's right. As you say
well,
here, yes.
No, I mean in the data that you showed us next.
Oh, here, yes.
Yeah, look at the data points.
Yes, right here.
They flatten.
That's
so
true.
It may well be not from the galaxy.
It's possible, and in fact, there's a paper that came out a month ago that suggests that there's from Yuval Birnbaum and colleagues that suggests that more of what we're accounting for is coming from the intergalactic medium as from the circumgalactic medium. Well, you have a larger box to account for that, or, I mean, part of it too, like part of it here is this only goes out to 300 kiloparsecs in this particular instance, whereas your virial radius is on the order of 200, 250 for a system like this. So it is possible to continue to go out beyond like 2 times the virial radius with observations or something like that to see it fall or to see where that plateau level is from the IGM. But you can account for this if you have a larger box to account for this larger region around the galaxy and the IGM's contribution. But part of it too is that the benefit of doing this with absorption line features is that they have a particular redshift, a particular line of sight velocity relative to that galaxy. And so if something is way, way in front of or behind the particular system, there's going to be Hubble shift and it's going to be way outside the velocity profile, so you can apply cuts relative to that.
Unless it's a cluster or a group.
Unless it's a cluster or a group. But primarily most of these observations try to do this for systems that look like they're not potentially part of that, or they separate based on environment. But this is a relevant question to ask as we probe these sorts of things. Liam?
Okay, so you underpredict the metals, but it doesn't seem like you underpredict the total hot gas based on X-ray SC and now FRBs. So do you agree with that?
In general, I don't think it's entirely. I agree that now when you start incorporating multi-wavelength observations like FRBs, like SC, and so on and so forth, you can start to probe what the hot gas contribution to all of this is. But I think it's a combination of both lack of understanding of what the diffusion of metals is and the metal in this environment, but also I don't think we have full closure on what the various phases of the gas are at all locations around the galaxy. Jesse, yeah.
Sorry, I realize we're taking so much time.
That's okay.
So if we're underproducing metals in the halo, then are there more metals locked up in the disk or in stars, or is there just overall less metals in the universe?
I'm not sure. I think in general from analyses that we are getting appropriate production of the metals. For these the fire simulations, at least this version of them, the Fire 2 models, which have been kind of the state of the art for the last few years, but now are being superseded by these new models that we're running now. it looks like there may be too little star formation relative to the systems. So that would lead to a lack of metals, but it's not just like those. No, those aren't even. Fire isn't even up here. This seems to be a universal problem regardless of the source of the simulation. I don't think it's just an artifact of one particular simulation. Yeah?
And is there any redshift evolution of the discrepancy between the theory and observation?
There is. There's a lot of redshift evolution for these particular.
Is it going to be better or worse as we go to lower redshift?
To lower Z, this is redshift like 0.2, which is appropriate for comparison with the Cos halos or Cos dwarf sample. These are redshift 2.5. I think this is redshift 2.5. You're seeing a deficit. You're seeing a tension at many different redshifts, unfortunately. There is evolution in the nature of the profiles, but you're still seeing tension at various different epochs. Okay, so why are simulations bad? Well, simulations are imperfect, of course, and they have a lot of shortcomings. But if we can understand those shortcomings, then perhaps we can use them as tools to better understand the nature of the system. So what is one reason that simulations are bad at modeling the CGM? So we try and make these models as simple as possible so that we can run them, right? And one way in which we make them simple is by increasing the computational expense in regions where there's more material, because that's what we care about, right? I don't care, well, some masochist might care about a void where there's nothing going on, and in some ways the CGM is kind of like that, but for the most part we care about the regions where there's more material because that's where we get data and we can make those comparisons. But both particle-based simulations like SPH intrinsically have more resolution in regions of more density, just by the nature of the mode, and grid-based simulations usually employ something called adaptive mesh refinement that increases your resolution in regions of high density. So either intrinsically or extrinsically, we tend to model things with higher densities, and the circumgalactic medium, which has low density, usually has very poor spatial and mass resolution. So, but resolution actually matters for modeling the small-scale structure. If I have a beautiful picture of a moon at night, and I degrade the resolution of that photograph where my resolution is coarser than the features that I'm trying to resolve, it's very hard to figure out what the heck I'm looking at, right? In a traditional adaptive mesh refinement simulation, this might look like the cosmic web that's feeding a particular galaxy in the center, and you intrinsically, as I said, have more resolution on the features of high density, but you're missing out on all this stuff around it. So what we can do, and I had some simulations a number of years ago that force the resolution to be finer in that low density material surrounding the galaxy, and just saw what would happen. So these are two identical simulations, one using a traditional AMR approach, adaptive mesh refinement approach, and you see the galactic disk, and then you see like very little stuff around it. In this case, we're looking at neutral hydrogen distribution. Whereas when I force the resolution to be higher, you see a lot more features. So colored here are Lyman limit or greater column density systems that should be observable. And then gray is more like Lyman alpha forest. And you can see a lot more content in the higher resolved case. So what's going on? These are, again, identical simulations. This is just more highly resolved than this one. And not only do you see finer features in this, which of course is expected, but you actually see more cool gas and more H1 because you're allowing it to continue to exist on these small scales, whereas it basically gets washed out and diffused in the case where we're unable to resolve it. So I'll not belabor this too much. If we make those similar radial profiles of the column density distribution, we see that the enhanced, what I call enhanced halo resolution, where we have finer resolution, allows a larger column density and a larger covering fraction of this cool gas. It isn't just my simulations. Freke van der Voort and others have done this using other codes, like this is using a repo. So that's all fine and good. If we increase the resolution, we see a higher covering fraction and more cool gas that can better come into, ease this tension with observations. But why? Again, these are all imperfect, so let's understand what's happening here. There's a lot more fine scale structure that's better probing kind of the phase space of density and temperature and basically everything. If we look at a phase diagram, density on the x-axis, temperature on the y-axis, you can see that because there are more fluid elements and they're more effectively probing the extremes of the phase relative to the coarse resolution run, and we subtract this one from the other and get kind of a residual of the two. You've got your coarse resolution kind of overpopulating this, 10 to the 6 Kelvin gas, 10 to the 5.5 Kelvin gas, whereas the high resolution is much more preferentially in the cool gas portion of the phase diagram. And what I propose that there's effectively two mechanisms at play here. One is resolution allows gas to cool from here to here, and it also preserves cool gas that's down here instead of allowing it to kind of drift back up to the coarser resolution. So if you think about a cool gas cloud, my little cartoon here, at coarse resolution or at high resolution. Coarse resolution is a single fluid element, so it has a single density, a single temperature, a single metallicity, whereas at high resolution it has a whole distribution of these various different properties. And if we put that onto a phase diagram of density and temperature, the cool gas, again, is just a big clump, but it has a single density and temperature and metallicity, whereas the fine resolution is spread out over the extremes of this. Now, that appears, at first glance to be relatively similar between the two, but this gas in the denser and cooler portion of the spectrum is going to be more prone to thermal instability and cooling, and so after a short period of time, that's all going to drift down onto this kind of 10 to the 4 Kelvin floor, and cause this disparity between a coarse resolution simulation and a fine resolution simulation. This is a movie from the simulations showing the production of a thermally unstable filament that's feeding the galaxy, and this is the phase diagram between the two. In the normal simulation, you essentially that gas is just kind of halo gas, and it sits in this portion of the phase diagram, whereas here you can actually physically see a filament that's forming because we've allowed resolution to do this. And so it drops by an order of magnitude in temperature and in density relative to its counterpart in a traditional simulation. And the other mechanism is, as I said, we can preserve cool gas by having finer resolution across your cool cloud. You preserve it and don't allow it to kind of numerical diffusion effects where it would just kind of phase away and turn into warmer gas. So these two effects, I think, are really pronounced and important, and it would be great if they were converged, but they're not, and they don't look like they're going to at any point soon. So what can we learn from them? If we just go through the process of kind of increasing resolution to try and predict, even though we aren't yet here at this infinite resolution case, we can get an idea of what to expect if we were to reach that point. And that's essentially what we see here. So as we go to higher and higher, finer and finer resolution, our cloud sizes become smaller, perhaps unsurprisingly. They become more numerous as we go to finer and finer resolution. And essentially the changes in the CGM are that we see an increasing number of cool clouds in the finest case. We see a decreasing size in them. We see an increasing covering fraction in them. And there's more effective cooling. So what does that point to in terms of like the infinite resolution, i.e. the real world, as being the answer? And it suggests that it might be composed of these like misty droplets of cool gas that are kind of just filling the overall halo in some sort of equilibrium with a hot component. So, yeah.
What are you assuming about the magnetic field? Is there some kind of reasonable magnetic field value that would effectively smooth out some of these fine structures that you're seeing?
Yes. So In the simulations that I showed for these Tempest simulations, they don't have MHD, but this has been done with other models that do incorporate MHD. And in general, the magnetic field doesn't seem to support structures. For these particular simulations, I'm only getting down to half a kiloparsec in scale. The magnetic field doesn't usually start providing pressure support until you get down to like parsec level scales for these cold gas structures. But that is a concern. What do additional physical processes, MHD, cosmic rays, how do they affect this overall balance between the various components? Yeah, John.
I mean, I agree with you about the pressure support, but what about like draping? So if you have some blob that's moving subsonically or superalphanically, so long as it's superalphanic, you're going to get magnetic draping that might prevent it from being shredded.
You can. That is true. But usually the draping effects, so when people have done cloud crushing simulations where you have, a cool gas cloud that's being slammed with a hot wind, and Phil Hopkins and myself and a student named Jihoi Lee did this a number of years ago with a bunch of different distributions and orientations and magnetic field strength to see how much it would preserve the structures. And it can hold things off, it can double the cloud crushing time, but it's not going to like prevent it indefinitely from destruction in the way that by increasing the resolution allows you to better preserve and not numerically diffuse these structures away. It helps, and it's important to account for, but it doesn't fix the problem intrinsically. Yes?
There is another effect, which is heat conduction and evaporation.
Yes, that's right. So thermal conduction is definitely something that we're trying to incorporate to test this. And both magnetic field strength, cosmic rays, and thermal conduction are going to affect kind of the convergence scale where the cool clouds appear to sit. Now, I guess I don't have it in this presentation, but there was a paper by Mike McCourt in 2018 that looked at, without magnetic fields, without any of these components, just he proposed the idea of thermal instability and gas shattering. Essentially, you've got a thermally unstable cloud, it starts to cool, it starts to collapse, and it shatters into many different small-scale structures. And this appears to converge at about 1/10 of a parsec scales, like tiny, tiny, tiny scales. But it's not accounting for effects like thermal conduction. It's not accounting for magnetic fields. And all of those are going to beef it up. They're going to cause that to be the minimum possible scale, this sub-parsec scale. Maybe it turns it into a parsec. Maybe it turns it into a couple of parsecs. But we're not seeing it yet at the kiloparsec scale. So somewhere in between is potentially where you find convergent scales for the size structures of these cool gas clouds. Okay, so lastly, and this is the stuff that's more recent as of this year, what can we do to better model the CGM? Now, in an ideal case, as I said, actually, here's the plot from Mike McCourt. I'm amazed that he got this hand-drawn figure into an AppJ paper, but the idea is that, thermally unstable gas will collapse and it'll shatter into, as I said, like parsec, sub-parsec size cool gas clouds. So of course what we'd like to do is have our resolution scale be as small as sub-parsec scales. That's not going to happen anytime in the next 100 years because if you look at hydrodynamic simulations, whether it's TNG or fire or whatever your favorite simulation is, the number of resolution elements that you're able to have in these fluid simulations is like, less than 1 trillion. And if you want to fully resolve a galactic halo that goes out to, let's just be modest and say 100 kiloparsecs at parsec scales, then you need, an order of 6 times more resolution element, or 6 orders of magnitude more resolution, not 6 times, that'd be pretty easy, but 6 orders of magnitude more resolution elements, so this is just not going to happen at any point in the near future. So what we can do as an alternative is come up with subgrid models to kind of parameterize the behavior of this small-scale structure from both simulations as well as theory, and plug that back into the large-scale simulations to better understand how these systems are evolving over time. So I've been part of 2 works that are trying this by kind of different methods. One, Irina Butsky, who's a Hubble Fellow now at Stanford, and I and Jess Work and collaborators put together something called the cold gas subgrid model. And that's the idea where you have a second fluid that sits kind of co-spatial with your primary fluid, your primary hydrodynamic simulation, and you have a coupling between the 2 fluids. So this one represents kind of an unresolved cold gas component, whereas your normal fluid is just the traditional kind of resolved, not cold gas. So we set this as fixed at 10 to the 4 Kelvin, since that's generally where this cool gas ends up because of the shape of the cooling curve. And we allow a drag term to go back and forth between the 2 fluids, and then we allow source and sink terms. So for a source term to this cool unresolved fluid, we allow for thermal instability, which is to say, hot gas that's thermally unstable. Each moment that it starts to radiate and cool gas away, we convert the hot gas away, we convert some of that gas into this unresolved cold fluid. And when we test this in kind of an idealized or few zone simulation, it generally is able to reproduce things that would be consistent with a resolved distribution, whereas in a traditional hydro simulation, you'd be moving along with your hot gas, and then all of a sudden you'd have a bunch of cold gas as the entire fluid element converted entirely to 10 to the 4 Kelvin gas, whereas this allows a much more kind of modest gradient along the time scale. And similarly, we allow a destruction of cool gas to hot gas via what we were talking about earlier with cloud crushing, and how cloud crushing simulations like this one, where we have a cool gas cloud that's being ablated by a hot wind, and it tears it up, but then it redistributes that gas behind it, which could then potentially convert back to cool gas. This is really interesting work that has been done by a number of groups, but I think most clearly by Max Gronke and Peng O, and show the evolution of that sort of system for a single fluid element. So at this point, the model is effective and reproduces things that under-resolved simulations cannot, but we haven't yet gotten it working with full cosmological hydro simulations with star formation and feedback and all the rest to test this on a larger scale. But I think it's a really promising technique. The other is this cloud flex model that I put out came out just a month ago, and that's a totally different approach. So if you've got your circumgalactic medium and you assume that it's composed of cloud structures of some sort, let's zoom in on a single cloud structure and see if by making some assumptions and making a kind of an analytic model for the distribution of gas in one of these structures and then repopulating the entire halo, if we can get some idea of what the observational signatures are of like a misty versus a clumpy distribution of cool gas in the halo. So here's our cloud structure. And what we're calling the cloud flex model, because it can be flexible as to various different parameters, we're going to make assumptions that this is a Monte Carlo method, that we're populating this larger cloud structure with different collections of cool clouds in a hot 10 to the 6 Kelvin bath, that each of the clouds has a uniform cool gas density, and that they're just spherical, and it's a spherical distribution, just for simplicity's sake. It has a number of different kind of input parameters that define the velocity phase in terms of turbulence, as well as the size and the distribution of those cool cloudlets. And we've tested a number of things that kind of cover the potential range of things that can be there. But most notably, our fiducial model looks something like this. So it's a power law distribution of cool clouds and their masses drawn from a power law with index of 2. And you can set what the minimum cloud mass is, so essentially how finely this goes. And you can do something like this. If you set your cloud minimum, your cloudlet minimum in this as very large, then it becomes a very clumpy distribution, whereas this is kind of a a median distribution, and then a very fine misty distribution. And when we do that, our misty, at least for the purposes of this, we're getting down to like parsec scale for our cloudlets, whereas in the clumpy, it's more like what these simulations have been able to do, kiloparsec scale. And if we reproduce the kind of behavior and send sightlines through this distribution, we can probe it for what observations might reveal. So we'll send a sightline through, and maybe in the clumpy case, it might only probe a single absorption or a single cloudlet producing a single absorption feature. This is essentially the cross section of the path through there. We might encounter 2 cloudlets, and you might get 2 separate absorption features with the black channel map representing what an observer would see as the collection of those void profiles. Or if you're going through a misty distribution, you might encounter many, many, many different cloudlets along that line of sight, each with their own respective radial velocities relative to the observer, and it might produce something like this that only looks like, it has like 3 or maybe 4 different kinematic components, but in truth is actually composed of, many, many, many different components. And we can get out the observables associated with this distribution, and then make a big collection of sightlines that go through each of these distributions, like 10,000 different sightlines, and put together probability distribution functions for number of clouds that are intersected for a misty distribution versus a coarse distribution, or the equivalent widths, or the covering fractions of these various things. And you can see that there is, we can garner some sort of insight as to what we expect to see based on a misty distribution of CGM stuff or a clumpy distribution of CGM. Clumpy being in green and misty being in kind of purple or lavender. You see a much broader equivalent width distribution than you would for just these coarse level green ones. And you see a much larger covering fraction. Yes?
Where is in the previous plot on the furthest right, where is the noise limit for observations usually at? So it's the next one. Next, yeah.
This one.
Equivalent width, yeah, what's the typical?
Oh, for here. Like how low of an equivalent width can we measure?
Yeah.
Milliangstrom. People measure things in milliangstrom. So quite small. So looking at, one thing is you can look at like what is the minimum equivalent width that you should observe, because for coarse level things, you're going to have a pretty large equivalent width. Whereas a mist, you can get down to the size of, the column density of a single cloud. Yeah, Liam.
Can you compute or estimate interstellar scattering?
I don't know. We haven't tried to do this.
You know what I mean? Like one of the predictions of a large covering fraction of these things is that they should scatter fast radio bursts that go through the sea.
Yeah, so certainly I'm working with Stella Ocker right now using this model to make predictions for what FRB, like diffractive scatter is, to give you an idea of what the scales of the density fluctuations are on like super, super small scales, like AU scales. But we don't have any results yet. But that is a super relevant question, and I know we're working on it. I know Kate Rubin and X Prochaska and Luis Masribas are trying to do this as well with diffractive scattering. Yeah. No, they're trying to do refractive, forgive me. So yeah, this is a relevant question, and it's something that we're trying to use this model to encapsulate. Yeah?
So getting back to the earlier set of questions, which of these clumpy versus misty would reproduce the radial profile of different ions better?
Okay, great question. So if I produce this kind of, if I create a full CGM that's composed of these different little cloudlet distributions, these cloud flex distributions, and I compare with a large-scale observational project that looks at, in this case, magnesium-2, which probes a cool gas phase. The simulations seem to prefer something, certainly not the clumpy, something like where your individual cloudlet minimum mass is somewhere around like 1 solar mass down or below. That's what is required to reproduce the equivalent width distribution with the Magic Hat sample as well as the Dutta et al. 2020 sample. So from this analysis, it's suggestive that it's more a misty distribution of cool gas that's kind of present in a hotter halo. But there may be, this is just looking at a particular ion, in this case the magnesium
And
2
if you
ion.
go to oxygen 8, for instance, would that be different because they are very hot?
Well, that's, when you get into the high ionization lines like oxygen 6 or 7 or 8, there will be some effects, but for the most part, the cool gas isn't playing as much of a role in that. It's unclear to me if increasing resolution, what factor it'll have on boosting that, but at least for the cool gas, I think resolution is, and a more misty distribution is definitely preferred. There may be other effects, as I said, like cosmic rays or something like this that might factor into this, or thermal diffusion. But, so yeah, what can we do to better model the CGM? We can create these robust subgrid models, and a misty CGM is kind of favored. So yeah, I was told to take 30 to 40 minutes, and I just took 50. So
That was a lot of discussion.
Thank you. So yeah, I'm happy to take questions and continue to discuss this. But thanks for listening.
Great. Any more questions?
Yeah, how much computational challenge would it be to just add a few more parameters to make the clouds elongated and random orientations? And could that potentially explain the mismatch in the outskirts of the galaxy? Because just the previous slide seemed like the inner part was well matched, but the outer radii are maybe a few orders of different.
Yeah, that's an interesting idea. We are looking at doing this for non-spherical cloud distributions, or non-spherical cloudlet shapes. It just introduces a lot more parameters is all, and at least at the 0th order, we were just trying to totally minimize the parameters associated with this, so it was an easier kind of problem to tackle. That might, I guess it could if there were a preferential orientation to the cloudlets. Magnetic fields or even like thermal draping. If you have if there's a hot wind, you're going to preferentially blow out the tails in a radial direction as opposed to perpendicular directions. So that maybe that would influence it as well. I don't know. That's a good point.
Any other questions?
Yeah.
Sorry. As a person that really loves Trident, I use it a lot.
Oh,
Are
that's
those
great.
misty ones are also publicly available?
The CloudFlex model?
Yeah.
Yeah, so the model that I described here at the end is open source. It's on GitHub. You can download this and use this to. I'm working with.
Can it be incorporated into Trident naturally, or is it a different one?
It can. There's actually a chunk of Trident that we ripped out to put into CloudFlex so that we could make these magnesium 2 observations that I was showing here. I'm working, so one of is Kate Rubin, myself, Drummond Fielding, and Evan Schneider. Drummond has his whole turbulent radiative mixing layer model that we're trying to incorporate into this so that we can, instead of just having 10 to the 4 Kelvin clouds relative to kind of a 10 to the 6 Kelvin bath, to have different layers like a onion skin of various different ions at intermediate temperatures and phases to represent these intermediate ions, and then seeing if we can use that in concert with these magnesium 2 observations to better constrain what the distribution is and what the predictions are. So there is, it's ongoing. There is part of Trident that's in CloudFlex. You can download CloudFlex and use it, and I'm trying to better integrate the two, but it's not there yet.
So you have this thermal instability operating, and it seems as if the observations prefer that it operate very well, and we end up with these very small clouds. But in what sense are these clouds? Because they're at 10 to the minus 3 solar masses. Is that just a numerical description?
Well, that's a fine question, because certainly the simulations can't get down to those scales. The highest resolution simulations, Dylan Nelson and Rahul Ramesh put out a paper in the last year, and they get down to a couple hundred parsec scales. So not nearly as small as these, oh, I thought I had, oh yeah. So in this MISTY distribution, it's down at the parsec level scale. Are these transient? Do they fritter in and out of existence? It's unclear. And because these models are Monte Carlo, like analytic models, this is a snapshot in time as opposed to following the hydrodynamics and the evolution of these systems as a whole. And so I don't have a good answer, but at least for the purposes of this is just testing at an instant in time what does the system look like, as opposed to how do these gas clouds behave over time. And
it seems like it's trying to go to a continuous distribution of gas rather than description in terms of clouds.
Oh, more like a statistical distribution. Yes, that's right. That's what it appears to be. At least from these sorts of analytic prescriptions that best match the observations. And so, yeah, I think that was a lot of the incentive for this cold gas subgrid model, is just having kind of an unresolved population of what you know how it's behaving statistically as opposed to individual clouds themselves. I mean, much like terrestrial clouds, atmospheric clouds, right? You don't think of the individual cloud droplets in a cloud. You think of the overall distribution and kind of its thermodynamic properties as opposed to the microscopic distribution.
Jake. Really nice talk. For the cold subgrid model, I was wondering what assumptions you make to go into what the cloud distribution is in the kind of unresolved cold scale. Does that depend on what's happening in the resolved hydro, or is it just kind of...
So for that, get back to it here. For that model, at this point, it doesn't really matter. It's just considered to be, for a single fluid element, it's considered to be uniformly distributed across that fluid element. This is done in ENSO, which is a grid-based code, so you have Cartesian grid cells, and you just uniformly distribute it across that. But you're right, one thing that we could do is, once we have galaxy scale simulations that are doing this sort of following the evolution of that cool gas, you could replace each of your fluid elements potentially with one of these more spherically distributed cloudflex that's more centrally concentrated. I don't know. I don't know the answer. What resolved small-scale simulations like cloud crushing simulations suggest is that there is some sort of central concentration, and then there's a mist around that concentration, and that if you take the mist out of context, then it'll effectively evaporate away because it doesn't have enough self-shielding or something like that from the photoionizing background. But as long as it's, this was originally posed by Peng O as the mothership and TIE fighter distribution, that there was, in order to have little, in Star Wars, there are TIE fighters that are enemy ships that fly around, but you don't see these just out in deep space. They have to be proximate to a mothership, to some sort of base, because they don't have long-range travel. And so the idea was proposed that perhaps cool gas cloudlets are the same sort of thing, that you can only have them proximate to a larger distribution and a larger structure of cool gas to essentially protect them and help self-shield them from the nasty intergalactic radiation field that could destroy them. So this is a long-winded answer to say, there are no assumptions that go into this particular model, but perhaps there should be, but we haven't reached that point yet.
What if instead, wouldn't you have a very similar results if instead of being misty, it was more filamentary, you have a different structure but with the same kind of distribution of small and big, right? For instance, in ISM, when they just model ISM isolated, right? And where they find is like 0.1 parsec. That in the end, they kind of figure out it was more like a resolution, so if they increase resolution, it will go even smaller. What they have is like, instead of like misty, is more like
Filamentary, like cobweb.
yes, like as if it was more
Cobweb-like.
fractal in a sense, right?
Mhm.
Because you could have like the same kind of distribution and shape, but like just at a different structure, right? Would you have a similar result for your?
I think it would have some similarities with the results that we're finding from this, and it makes sense too. I mean, you think about self-similarity on large scales, and you think about the cosmic web having that. Of course, that's mostly driven by gravity, whereas when you're in these galactic halos, the gas fluid elements are so low mass that much of what's confining them is thermal pressure as opposed to any kind of gravitational collapse that's undergoing it. So I think there would be some similarities by having high resolution, finer particles that are collated in some sort of filamentary structure, but I think there'd be enough of a difference that you wouldn't see the covering fraction. Oh, I've got so many darn slides. It's amazing. You wouldn't see as great a covering fraction if things were preferentially aligned along filaments as you
Right,
do.
but then it's 3D, right? So in projection.
Potentially. I think it's certainly something worth taking into account for reasons that were just addressed in this TIE fighter. You know, if things tend to be more clustered, then what is the preferential clustering that's dictated by the medium and the radiation field that's causing that? So it's possible. This was just like a zero order approximation for it based on spherical symmetry.
Okay, awesome. And it's noon, perfectly to the second.
Okay.
We should stop here. Let's thank everyone again.
Thanks.
Those at least one.